Okay, so since you mentioned the dose effect relationship, that's what we are going to do. We'll move from there. So basically, the dose effect relationship basically tells how the effects of a drug will change if you either increase the dose or decrease the dose. You get it? So basically, all that we know is that if you increase the dose, like paracetamol, if you take two, the effect will be higher than taking one. You get it? But this one we are going to analyze it with graphs so that we will appreciate it more. So just as it was stated, as the concentration of a drug increases, the magnitude of its pharmacological effects also increases, and it's been indicated here with this graph. You can see that the dose is here. This is the dose effect graph. The effect is vertical, it's being placed vertically, and then the dose is here. You can see that when the dose is increasing, the effect also rises. So this may be dose 1, let's say 1.0, this will be 2.0, this will be 3.0. So you can see that 1.0 will be like 0.4, 2.0 will be like 0.7, and then 3.0 will be like 0.9. You get it? So basically that's a rule of thumb that as you increase the dose, the effect also increases. Now, um, so this one is showing one is a linear relationship and the other is a non-linear relationship. But actually, what happens is in humans or in biological systems, it's actually a non-linear relationship. Okay, and we'll look at why it's a non-linear relationship. So if it's a linear relationship, then it means that when 50% of the receptors are occupied, then we should get 50% of the response. You get it? That's what the linear relationship is. So in humans, we don't have that ideal system. Okay, so we'll look at that as we continue. So with a dose effect graph, actually, when you are conducting an experiment, this is the graph that you get. Okay, so this is so you plot the dose against the effect. Okay, it's the same thing here, just that this one is the logarithm of the dose. You get it? The logarithm of the dose usually is better than plotting the dose itself. So you get the dose. Let's say I gave it 1.0 grams, I gave it 2.0 grams, I gave it 3.0 grams, and then you estimate the effect that was produced. You get it? Aha. But if you use the logarithm of the dose, so you see you were given 1.0, 2.0, 3.0, so you use log 1.0, log 2.0, log 3.0. As we move further, we'll know why that seems better. So it's actually this graph that we have. Okay, so this is the arithmetic scale, and then that's the logarithmic scale. You get it? Yes, the arithmetic scale has its own advantages, but then the logarithmic scale has more advantages as compared to the um, arithmetic scale. You get it? So you as we go on, you get it. So with the now we are just opposing both of them. With the arithmetic scale, the first one is that you see a rapid change at first and it becomes progressively smaller as the dose is increased. So let's go back. You can see that immediately we gave the animal some drug, the effects increased nti zero no effect. By a bar, yɛmfa no sɛ yɛba a bɛyɛ 5 na effect no ahwiti akɔ bɛyɛ 0.3 na yɛsan increase ne kɔɔ yɛmfa no sɛ 7 a na effect no akɔ bɛyɛ 0.5. You can see that initially it increases. So when you start, the more you increase the concentration or the more you increase the dose, the more the effects increases or the more effects the patient shows. You get it? But it gets to a point that it begins slowing down or it begins to slow down or the curve begins to flatten such that even if you increase the dose, there isn't so much of a change. And this can be explained in terms of the fact that we know that these receptors are protein in nature, and since they are protein in nature, um, they can be saturated. Okay, so you gave, let's say, 50,000 molecules. Okay, the ones that you gave, all the receptors are occupied. So they would have to wait. The drugs have to wait for the receptors to be released before they are able to bind to the receptors again. And that would account for the fact that even if you increase the concentration, it wouldn't increase the effect. You get it? That is why we have this kind of curve. Okay, this yama yama curve. And then, okay, let's just oppose them. Eventually, increments in dose produce no further change in effect. That is, the maximal effect for the drug is obtained. So you can see that the curve has started flattening here. It will get to a point it will flatten such that even if you move the concentration from 80 to 100, the curve will still be flat. So if the effect is at zero point 0.9, or if the effect is, let's say, yes, zero point 0.9, it will still be there. Even if you increase the concentration up to 1000, it will still be at zero point 0.9 effect because all the receptors are occupied. And as such, you wouldn't see any effect. You get it? That is the arithmetic skill. Okay, and that is actually what happens. Okay. And one disadvantage is that it's difficult to analyze that kind of graph mathematically. Okay, yes, we would know why it's difficult to analyze mathematically. Okay, so with that said, let's go to the logarithm dose scale. So it's this very scale that we have converted it into a logarithmic scale. You get it? So just take these specific values and then keep them into logarithm. So if it's 20, 40, 60, you can just put them into logarithms. Okay. So the first thing is that it transforms the parabolic curve to a sigmoid curve, and the sigmoid curve is almost a straight line. So it's this parabola that has been transformed into this sigmoid curve. Okay, you see that this one, they have written that this area is nearly linear. Okay, and linear curves can be studied very well as compared to this one, curves. Okay, so it's easier to study linear curves than um curved ones. Okay, linear graphs are easy to study. Okay, so it straightens the line. We can see that when you plot it as a logarithm, this side becomes somehow straight, and that makes studying very easy. And then it's easier to analyze mathematically. It compresses the dose scale. So we can see that these values are 20, 40, 60, 80, 100. But these ones are in steps of 10. Okay, so 0.1, 1, 10, 100. Okay, so from 100 we'll go to 1000. From 1000 we go to 10,000. As compared to 20, 40, 60, 80, 100. You can see that this one would accommodate more values. And since it can accommodate more values, you know that these drugs, we give them in nanomoles, nanograms, and stuff. These are very small units. You get it? So since they are very small units, let's say you have given 10 grams and you are starting from nano, you would need um if you are using this curve, you need to draw, like, your graph will be so long. You get it? Let's say you started from nano, 20 nanogram, and what they basi fan is a basi 10 grams. You see, you would have to move from nano, you have to go to micro, milli, and stuff. You get it? And that would prolong your graph. And even with that, you wouldn't be able to make any good judgment. Okay, that's why this one is better. So this one you can easily switch from that nano into the normal grams. Okay, because it compresses the dose scale. And see, you can even analyze higher doses. You see, so from here you go to 1000 nano. these are moles, so 1000 nanomoles as compared to 100. So you go to 120, 140, that be now be do 1000 nanomoles. You get it? Good. And then proportionate doses occur at equal interval. That's good. So we know that this one is being transformed into a line, right? And you know that for a straight line, it has almost a constant gradient. And since there's a constant gradient, the gradient here will be the same as the gradient there. And so if you have a value here, you can use it to predict for the dose here. Or if you have a value there, you can use this same graph to um analyze whatever is going to happen here. You get it? So proportionate doses occur at regular intervals. So it means that from here to here, if the lengths are the same, then the difference between this and this, the dose difference, will be the same as the dose difference between this and that. But that is not seen in this skill, the arithmetic one. Okay, you know that for a curve, before you can find its gradient, you have to get the tangent at this point. You get it? And getting a tangent at this point means the gradient will be different from this side. Here it will be different, there it will be different, this side it is going to be different. You get it? So it will be difficult for you to be able to predict whatever is going to happen if you don't have the full graph. Okay, but with this linear graph, if we convert the arithmetic scale into a linear scale to be able to analyze it mathematically, we can use our graph to predict whatever is happening. And you know that this is pharmacology. Um, some of these researches are done in human beings, and in humans, you can't wait for the person to die before you know the dose at which they died. What I say? Aha, but if you have transformed it into a linear graph, you know that, oh, at this point, all these receptors will be filled up. The person may die. This is a toxic dose. You get it? Aha. So you can use that to predict rather than using this curve. Okay, that's why we say proportionate doses occur at regular intervals, and it's easier to analyze mathematically. Okay, because you can easily use that to make predictions. Okay, so we are going to potency. Let me pause here. I don't want to make it long, so that in the next video I'll just touch on potency.